Okay, so here we're gonna demonstrate an example of an if and only if statement. So here's the if and only if in this case, and we got to understand what it means to say if and only if, right? So you have this statement. It says, let x be a real number. And it says that the floor of x equals the ceiling of x. So this is called the floor, right, of x. And then this is called the ceiling of x, and we'll define these ideas. If and only if, also written like this sometimes with a double arrow. If and only if x is an integer, x is contained in the integers, whereas z stands for the set of integers. So in order to prove an if and only if statement, we need to understand what's actually being stated here. It's two things that are being stated. It's really two statements in one. It's if, right, the floor of x equals the ceiling of x, then we know x is an integer. Now that's one direction, right? And the other direction, if x is an integer, then the floor of x equals the ceiling of x. So let's work on doing this. We need to prove it in both directions. This is the same statement, right? You need the if and only if just means exactly this, right? P if and only if Q means if P then Q, and if Q then P. The implication goes both ways. So we need to prove the implication in both ways. So let's start off with one direction. Let's prove this one. If the floor of x equals the ceiling of x, then x is an integer. X is contained in the integers. So to prove this, we say let the floor of x equal the ceiling of x equal n for some n contained in z, right? Because what is the definition of these things? So the ceiling, or the floor of x, right? The floor of x is defined as, right? And this is just going to be a nice set of words, defined as the greatest integer less than x. Less than or equal to x. Greatest integer less than or equal to x. So then that means that we have that this equaling n, right, means this immediately implies from the definition that n must be less than or equal to x, right? And then similarly, the ceiling of x is defined conversely, right? Is defined as the least integer greater than or equal to x. So this means that if the ceiling of x is equal to some integer n, then this immediately implies from the definition that n is greater than or equal to x, right? But now we have this statement combined with this immediately implies that n equals x, and x is an integer. Okay, from these two, right? These two statements, let's say this is 1, 2. 1 and 2 together imply that n must be x. The only option for both of them being true is that n is x. And that's one direction, right? We proved this direction. Now you got to do the other implication. So the other way is that if x is an integer, then the floor of x equals the ceiling of x. Okay, so to prove this, right, we say if x is an integer, then what do I have? If x is an integer, then the floor of x equals x. And that just from the definition, right? If x is an integer, right? What's the definition of the floor of x? The greatest integer less than or equal to x, but x is an integer, so it's the greatest integer equal to x in this case, right? Which is just x. And similarly, it should be obvious that the ceiling of x is just x as well for us, similar by definition of the ceiling of x, and then this would just imply that these two are indeed equal. Okay, you could say by definitions. Right, by the definitions of floor and ceiling, this kind of becomes obvious. I mean, again, read the definition carefully. The floor of x is the greatest. If x is an integer, right? Think of it like this: 4, right? What is the ceiling of 4? What is the floor of 4? Well, it's the greatest integer less than or equal to x. So is 4 less than or equal to x? Yes. And is it the greatest one that's less than or equal to x? 4, yeah, it is. And then the ceiling of 4, right, is the least integer greater than or equal to, which is, again, just 4. It's the smallest integer less than or equal to 4. Anyways, so yeah, these statements just sort of follow intuitively from the definition, and then you have the result in this direction, and then you've proven it in both directions. So the implication went both ways, right? If and only if you proved it in one direction, this is the one direction, right? This is, let's say, one direction, and then this is the backward direction, let's say, the forward and backward, and then that's it.